Okay, well, it's my pleasure to introduce Mike Heroux, who is a senior scientist at Sandia National Laboratories. He also serves as the Director of Software Technology for the DOE Exascale Computing Project. Mike is also a scientist in residence at St. John's University in Minnesota. He researches all aspects of scalable scientific and engineering software for new and emerging parallel computing architectures. He also heads an integrated effort to provide the Exascale Computing Project Software Stack. Mike leads several other initiatives, which include the Trilinos project, which provides reusable, scalable scientific software components, and he also leads HPCG, which is an official top 500 benchmark for ranking computer systems, the leading edge computer systems in the world. Dr. Heroux has a PhD and master's degrees in mathematics from Colorado State University and a bachelor's in math from St. John's University. So welcome, John. Not John, Mike.
All right, thank you. Thank you, David. Can you hear me? All right, thank you, David. All right, so this morning I'm going to talk to you a bit about, for those of you who were here last year, I spoke here, so nice to be back. Talk about a different topic this time, related but a little bit different, and hopefully leave you with some ideas that you can chew on a little bit as you stay here and then go back home. The Exascale Software Stack is a collection of products that we're developing for Exascale Platforms. And if you're not familiar with the term Exascale, that's been thrown around, it's become a buzzword, I think. But it stands for 10 to the 18 operations, guaranteed not to exceed speed, let's put it that way, of the computer systems that we're building today. So let me talk a bit about that and some thoughts around that. Okay, so I know it's summer vacation, but you are at a conference, and so I thought it would be worth giving you a quiz. Okay, and it actually, so I give my kids homework over the summer. In fact, I expect to receive a text from my two sons from their math homework. When I travel, I make them take a photo of the assignment page and what they wrote for their answers, and then I grade it by text. It actually works pretty well. So I expect to hear something about friction today from one of my sons, and then a little on geometry, simple proofs using geometry. Anyway, so here's your quiz, okay, and we'll go through the answers at the end. Exascale systems will have more network-connected nodes than any previous supercomputer. So this is true or false. You think about your answers. You don't have to answer now. Top performance on an Exascale platform will require roughly billion-way concurrency. Every computational scientist will need to know how to write task parallel code. Every computational scientist will need to know how to write vectorizable code. The MPI part of MPI plus X will be the most challenging for Exascale platforms. The X part of MPI plus X, where X is things like OpenMP and CUDA and so on, will be the most challenging for Exascale platforms. As a computational scientist, in the future, you will likely be working as part of a large team. As a computational scientist in the future, will be likely working as part of a small team. The term United States is plural. Okay, that'll make sense at the end, I hope. Gardening is relevant to leading large, gnarly projects like the Exascale Computing Project. All right, so let me give you a little bit of background on the broader context of which ECP is part of. Okay, so the ECP is part of the Exascale Computing Initiative, and a few years ago, President Obama made a big announcement about this initiative, and so this has crossed the United States government, involves many agencies. ECP is a part of this. It's one of the 4 big parts of it. And so I just want you to know that even as I talk about what I think is a big and gnarly thing, it is actually part of a bigger and gnarlier thing. Okay, so sorry, my screen is kind of acting up. I'll have to look up here with you. Okay, so ECP is a critical part of this broader ECP's US Exascale Computing Initiative. These are some of the activities associated with it. Again, I'm not going to go into a lot of detail. These slides will be available, but I want to show you what is here that sits on top of what ECP is. ECP is also a collaboration among primarily 6 US DOE national laboratories and a bunch of universities and industry partners as well. So we have a lot of people involved, a lot of institutions involved, a lot of cultures involved in the activities that are going on within ECP. It has 4 primary components: the hardware and integration, software technology, application development, and then for me and for many people involved in ECP, there's a project management element to it, which is quite new for us. We're not used to talking about things like CPI, right? Things like that. These are new sets of acronyms for us that talk about costs and earned value management and new terms to us. And so we're learning and grappling with these concepts and how they can be integrated into a scientific software, scientific computing effort. The hardware and integration top area has 5 different areas, sub-areas within it, and these are all what are called work breakdown structure. They have codes associated with them. So we're working with 4 levels of codes within ECP. Hardware and integration is responsible for interfacing with the facilities, interfacing with the vendors, making sure that ECP efforts are coordinated with other people who are producing exascale capabilities. Software technology, the area that I lead, has 5 different areas, and each of those has a lead, and then within those are many other projects. We have, in fact, a total of 55 small projects within the software technology area, and I'll tell you a bit about those as we go along. Application development has a variety of areas as well. And then project management, as I mentioned, has a variety of areas. And these are people who pay attention to our costs, try to help us identify value, where we create value, how we can account for that value, how we spend money, and how we can account for the progress of creating value against the expenses that we have incurred to create that value. In addition, ECP is eventually targeting exascale platforms. So this drawing here is a collection of the machines that some of which we know about in detail, some of which have been in place for quite some time. You may have heard, if you pay attention to this, the 2 recent systems, Summit and Sierra. And in fact, just a few weeks ago, they were announced as the top 2 systems on the top 500, and are now quite a bit in the news. But there are new systems coming along, and the ones to the right are the newer platforms that we are targeting within ECP. We're trying to produce the software stack that will make these systems effective. A lot of the effort that goes into ECP software development is targeted towards the applications that are funded for exascale computing capability. So we've signed up for specific science modeling and simulation objectives with ECP, and the software that my team provides in terms of things like message passing interface, MPI, mathematical libraries, data and viz tools is all intended to help support the applications that are supposed to run on this system. This is just a schematic then of the areas that we're attacking with exascale platforms. Each of these areas is expected to benefit in the terms of its science, ability to understand new science and engineering by the availability of an exascale platform and the codes that we're targeting for these platforms. In addition, Katie gave a very nice talk about AI. We're trying to blend, and this is relatively new for ECP. This is a new activity that's starting up within ECP to provide AI integrated in with modeling and simulation, as Katie described, the new capabilities, new opportunities for us because we have artificial intelligence, machine learning, deep neural networks that we can use to improve the quality of what we're trying to do. And so we're standing up new capabilities within the software area to support these activities. And here's one more associated with that. Okay, so that's a bit of background. So I tried to bring you from ECI to ECP and then the 4 areas within ECP, and now we're going to go into software technology. Okay, so I burned quite a bit of my time just getting us down to what I really want to talk about. But let's get started here. Okay, so ECP Software Technology is a collection of 5 basic technical areas. The data and visualization you'll see in the top, and then there's embedded data and visualization. That's one of the technical areas. This has to do with how do we manage, how do we interpret the data that are generated as a part of our simulation activities. That's one area. The software ecosystem is, for some reason this one, okay, the one that's blank is programming models and runtime. My machine is having a little trouble. I have a new Mac, and it's maybe not as good as the old Mac. So I apologize. Programming models and runtimes is the empty square, empty rectangle that's there. And that is where we're developing the next generation of MPI, compiler assistance tools, interacting with vendors to produce compilers, enhancing OpenMP for being able to do on-node parallelism, and so on. Development tools are tools that help us get insight into how our codes are behaving, how to improve their performance, how to improve memory and data layouts and such. And then the mathematical libraries include things like PETSI and Trilinos, SuperLU. These are libraries that you can link to use to accelerate your simulations and get answers to very challenging problems. Then the underlying layer, the pink layer, software ecosystem and delivery, is our interface to the rest of the community. So we have to make products, and we have to deliver those to other people. And the software ecosystem and delivery areas is what does that for us. Okay. So our efforts within ECP Software Technology are, you might think, Exascale is big and forward-looking, but we're actually fairly conservative in our approach to doing things. We have a very tight timeline to deliver these capabilities, and so we are not the project that is looking at the next kind of groundbreaking parallel programming approaches. We're trying as much as possible to extend MPI, the message passing interface, extend MPI plus X, where X is OpenMP and CUDA, to make that work as well as we can going forward. And the reason for that is that if you start to introduce disruptive programming model and execution model changes into your system, you now have to re-architect the applications. And so, which we will need to do. There's no doubt that we will need to do that. But we're trying to extend our current application architectures as much as we can, get the most value from them where we can. And so that's a major thrust for ECP. We are performing R&D where needed. We have to do some, and we have to invest in some disruptive technologies, if for no other reason, to make sure that we're informed, so that when we go beyond Exascale, that we are prepared for that next post-Exascale capability. So we have to know what is being developed for post-Exascale, and we have to make sure the work that we are doing is compatible and can integrate with that. We also need to work with our vendors, and so we have very frequent conversations with companies like Intel and Krell, IBM and NVIDIA, to make sure that our plans and their plans are compatible and complementary as much as possible. And then a strong focus with ECP, not that we've written bad software in the past, but we're trying to elevate the quality of the products that we produce. We're trying to help developers be more productive and help make the products that we make easier to sustain, more sustainable. Okay, so what are our challenges? Billion-way concurrency. Hey, are you paying attention to the quiz? Here's one of your answers. Pay attention. Billion-way concurrency. So we have several new node architectures. One of the novel things about computing right now is that parallelism is not necessarily coming from lots of nodes, but from parallelism within the nodes. And so the X part of MPI plus X is the growth area. Vectorization, tasking, all of these things, that's where we're seeing a lot of growth. We're not actually seeing a huge increase in the number of nodes. In fact, a bit of a reduction in the number of nodes. Okay, that's another answer. All right. We're also data-driven in a lot of our capabilities. We're investing in new HPC environments. We're investing in container technology. We're investing in the integration with artificial intelligence. We're also part of this an ecosystem, a very large and complex and evolving environment. Okay, so that's some of the challenges that we face. Within the structure of Exascale within the US, we have ECI, we have ECP, and then software technology. And so we're WBS 2.3. And then within that is 2.3, 1, 2, 3, 4, and 5. And so this is the structure. This is the leadership team. Myself as the director, Jonathan Carter from Lawrence Berkeley is the deputy director. And then we have Rajiv Thakur, Jeff Vetter, Lois Kerfman, McInnes, Jim Ahrens, and Rob Neely as leaders within each of the technical areas within ECP. These are all senior people who have had a lot of experience developing and leading scientific software projects. It's a really great team of people with whom to work. So, okay, what are some of the specific key themes in each of the areas? Okay, so MPI plus X I mentioned already. Message passing, distributed memory, and then executing something parallel underneath each MPI process is the model that's dominant in our applications. It's one of the key focuses for us. But it actually turns out that the plus between MPI plus X, the interface between independent processes and the parallelism that occurs underneath those independent processes, that's the hard part. What's the interface between those two semi-independent approaches to getting parallel execution? So it's actually the plus of MPI plus X. Bill Gropp has made note of this in many of his talks, if you know him. And that is actually the key. That's the key design point. That's the key aspect of how do we get the best performance out of our existing application bases, getting the plus right. We are certainly promoting standards. That's a very important activity. We also are investing in portable expression. You may have heard of products like Raja and Cocos that allow you to express node-level parallelism in a way that is then mapped, transformed to specific execution on a given node type. We have new and deployable programming models. There's efforts going on in Legion, for example. And then extension of our core environments that I've already mentioned. Development tools. One of the nice ways to write new code is to have the machine do it for you. And so we have efforts that are going on in code generation, taking simple expressions and then going from source to source. Capabilities like analysis tools. What is my bottleneck? Why am I not scaling? Questions like that are addressed. And then adaptation to new architectures and then performance analysis on these new architectures. In the math libraries area, performance on new node architectures. Math libraries are often the first people who have to try to deal with new node architectures and get the most performance out of them. For example, at Lawrence Livermore National Lab, the Hyper project, they're dealing with GPUs. They have a new platform, Sierra, and that requires them to make effective use of GPUs. And so they're exploring this and trying to understand it. Two of our new programming execution constructs that we have to worry about are tasks. These are independent parallel streams of execution. And then vectors. Now with tasking, as we evolve our codes to be effective at tasking, most of you will not have to necessarily write tasking code. You will write code that executes within a task, but you yourself will not have to deal with the task dispatch layer. I'm guessing, that's my prediction. Much like if you work within an MPI code right now, you do not actually deal specifically with how does code execute across tens of thousands of processors at once. You need to know that that's happening, but generally you write just the process code that executes under MPI. So, but vectorization is more difficult. It's hard to hide that from a computational scientist. You actually need to know what vectorization is, and you need to write your code so that it is vectorizable. So that's actually something that you will have to worry about. SIMT is similar. So those are concepts that if you don't know them, you should learn, because they're important for you if you're going to write high performance code in the future. We also care in the math libraries about extreme strong scalability. Often the solve part, the linear system, if you will, that you're trying to solve is just one piece of a much larger computation, and so it may be a bottleneck, but it's for only a portion of the data, and so that has to be as fast as possible, and you can't just simply grow it to the full size of the machine because it's not important. That's not the important part. You need to solve a small problem as fast as possible. We also have to deal with advanced coupled multiphysics and multiscales. In fact, a common theme across the applications within ECP is bringing multiple types of physics, multiple scales together and solving them, resolving them at the same time. That's an important use case for these very large machines. Optimization, UQ, and solvers are similar, and then interoperability, which I'll talk about later. All right. Data and visualization, hierarchical storage systems are a big deal. The introduction of non-volatile memory into the fabric of the machine is an incredible boon for us, a great technology advancement, but it also brings complications. We have to figure out exactly how to use this, the different models and different approaches. Adaptation to new node architectures is really important, data compression and warehousing and in situ visualization, and then novel visualization approaches. One of the new workflow items for many applications is before they write data out to permanent storage, they might want to do something with it. They might want to look at it. They might want to compress it because maybe they can't write it out fast enough to the permanent storage. And so, although this has certainly been done in the past, we see an increase in this phase of the work cycle, life cycle of computation, that you compute, you produce a lot of data in memory, and then you don't just write it out now. You try to look at it, you try to compress it, you try to make something meaningful from it actually before you write it out. So that's an increased effort within ECP. And then I mentioned software ecosystem and delivery. We have to deliver what we are developing. And it requires new levels of collaboration and coordination. And there are new ways to do this. Containers provide us with a tremendous technology for delivering capabilities in a way that we've never done before. And so we're trying to understand and characterize the value of containers as we go forward. All right, let me talk a little bit about ECP SD products. Okay, so I mentioned there are 55 projects within the software technologies in ECP. We did a census of the activities, it ended in April, and those 55 projects contribute to 89 unique products, meaning that the efforts of ECP Software Technology are contributing to 89 products that are out there. Some of them are new, some of them are old, some of them you'll know quite well. How we deliver them, most of them have a delivery path directly to the developer. They have a repository that application developers can access. They can take the source code from that repository, build it themselves, and link to it and go. Some are in the vendor stack. Vendors actually take some of the software that we produce and put it in their stack. All of the facilities take some portion of what we produce and include it in their stack on their platform. So at Sierra, at Livermore, at Summit, at Oak Ridge, there are ECP software technology products that are built and supported by the staff at those facilities. We also have an ongoing and perhaps growing relationship with OpenHPC. OpenHPC is a special Linux distribution organization. So if you're familiar with other Linux distributions, SUSE or Debian, this is a special one that is focused on products that people who are doing high performance computing need. We're establishing some interactions with them so that we can work with them to deliver binary and source RPMs. And then containers is a new area where we're working. And other things are important there too, but I'll just move along. So, as I said, there are 89 products, and I'm not going to go through all these in detail, but I want to just show you again, these will be in slides. Now, I've highlighted some of the products you actually might know. You might know MPitch, OpenMPI, LLVM, OpenMP, GasNet. So if you've been involved in parallel computing, you may know some of these products. There are other ones too. I didn't want to highlight all of them, but these are some that you might know. Same thing in the development tools. SCR, Scalable Checkpoint Restart, PAPI, performance interface, HPC toolkit, Dynast, Tau, again, LLVM, different aspect of LLVM. In math libraries, Hyper, MFEM, Trilinos, Sundials, PETC, SuperLU. These are all codes that if you've been involved, you probably know them, and that we're contributing to and trying to get ready for Exascale. Similar thing in data and viz, similar thing in the software ecosystem and delivery. So these are all of the products. So the next thing I wanted to talk about was, okay, so we have all these products. How are you going to organize this? How are you going to pull all of these things together? So one of the organizational directions we're taking with ECP is what we're calling SDKs, Software Development Kits. What we're trying to do with SDKs is create aggregates of software capabilities that are similar or provide similar functionality, so that if you're a user of one product and you want to try a similar product, it will be easier for you to switch over from one to another. Or if you want to use them in combination, you'll be able to do that. This approach started for us within the math libraries about 4 or 5 years ago with what we call the XSDK. And I mentioned this last time, but now what we're doing is we're extending this basic strategy to all of the ECP software products, so that we can create aggregates of software capabilities that have a similar domain scope, where there's a non-trivial interaction between them, where we want to develop community policies. We want to develop some infrastructure, coordinated plans, and coordinated community outreach to try to get unity in the things that are essential while otherwise allowing diversity. And so the first instance of this and what we use to train our minds and build our strategy is the so-called XSDK. So we have these libraries, PETC, we have Hyper, Sundials, MFEM, SuperLU, Trilinos, and these libraries are all in a certain way providing solution for systems of equations. Now what we're trying to do is make them so that they're interoperable, so that if you want to use them together, if you want to use one instead of the other, that you can do that. I'll give a concrete instance is the ExaWind project, is a wind farm simulation project. And it is trying to develop models that look at the interaction between wind generators in a large farm, right? Because that interaction is not well understood. So a core element of that is actually solving a linear system of linear equations using multigrid. And they were struggling with one of the solvers that was being used. But because of the XSDK, they were able to swap in the other solver, another one. So the Mulu was the one that was struggling. They weren't sure why. They were able to bring in Hyper and try it and be able to play around and explore the possibilities. Two good things came out of that. One is they got a better characterization of the challenge, and the other is it created a little bit of co-opetition between these two teams, which I think is a positive thing. So anyway, so you can see that having these SDKs, at least from within the math libraries area, is a very positive thing, in my opinion. In addition to the actual interoperability of these packages, we also developed what we're calling community policies. And these policies are, in a sense, expectations of the behavior of the development teams. Not only does it help the teams know what the baseline behavior and best practices are, but it also serves as a set of requirements for anybody else who wants to join the SDK. So you had a number of teams who've joined, want to be part of this XSDK, and we say, look at these community policies. If you satisfy them, then you can become a member. And it becomes that kind of directive for how to become. So we're extending this SDK notion to all of the ECP software stack. We have a team of people who are, again, decades of experience in scientific software who are leading this effort. And we're going to be using these SDKs as an intermediate aggregation point for things like planning, being able to build collections of software, being able to coordinate and provide what our capabilities are. So we're extending this. We're using a tool called SPAC to help us manage the packaging of these software products in the SDKs. We're very pleased so far. Although this is a relatively new effort, we're very pleased with our efforts in this area. What are some other important ECP ST contributions? Well, I mentioned that we belong to standards bodies. So a number of our team members contribute to the key standards. If you want something to be sustainable, get it in a standard. Get the API defined, and then you and others who want to provide that capability simply have to provide an implementation to that standard. So that, for you, in your future, should be an important part of what you do. This is a key way to make what you do sustainable, is to participate in standards. Not just MPI, which we own as a community, not just OpenMP, which we own not totally, but we're a big part of, but also C++, where we are a tiny member, right? We are a tiny member of the C++ community, but we know high performance, and so we can inject into the C++ standard the ideas that help high performance be a part of what C++ is. Same thing, Fortran, OpenACC, LLVM, these are all things to which our members of ECP contribute. Also, and this may not be so widely appreciated, the best way to write a piece of sustainable software is to let somebody else do it for you, right? Okay, so unless, I like to write code, I really do, but I don't like to support code, I'll tell you honestly, right? I would rather have somebody else do that job for me, right? And I'm high enough up now, somebody else does it for me anyway. They have to deal with all the mistakes that I made a decade ago, they are dealing with right now. And I'm sure they say things behind my back, but they're kind enough not to say it to my face. But the best way to have a piece of software be sustainable, the best investment we can make within ECP, if possible, and we can't do this all the time, is to actually do requirements gathering, analysis, and design, and maybe write a prototype of that software, but then hand it off to somebody else to actually make a product out of it. And we have some of these activities going on. And I want to highlight this because I think it's an important contribution that DOE more broadly and ECP provides to the community. Okay, so I said a lot about this stuff. It's fairly complicated. I just want you to know that this is all written up somewhere. So if you want to actually go and read more, and in fact you can get of the 55 projects, you can see a couple-page summary of each one of them in this document. It also gives a highlight of the overall strategy of ECP Software Technology, the product breakdowns that I showed you, and our philosophy and strategy for managing the project, so you can go take a look at this. There's a public version of it, has about 191 pages, and it's available from the exascaleproject.org website. All right, so what did you learn from all this? Well, I hope one thing appreciation you've had is that leading a project like ECP Software Technology has the following characteristics. It's big, it's complicated, it might even be complex in the sense of mathematical complexity, and that it has emergent behavior, things that you could not have predicted, things that are below the scale that you're modeling, right, that really you can't have known about. So how do you deal with that? Right? How do you deal with that? And I'm going to tell you about a particular way, not because I'm trying to promote it, but I just can't talk about this without giving specific, concrete examples. Okay? So there's a very nice book called A Team of Teams. I really like. Took is shaking her head down, my program manager. But I like this book, and I like the approach because it evokes really good ideas for me. And it actually inspired a lot of how we've organized things within ECP Software Technologies. And it's not, I don't recommend it as a kind of Bible or scripture, but I recommend it as a way for you to start thinking about hierarchical organization of teams and where you might fit in to this kind of approach. So small teams are critical, right? We know that. You've been involved in small team activities most of your life. We can point all the way back in history of HPC, high performance computing, to specific small teams that really made a huge impact on our community. These are just a few examples. Right, but you know that approach works because that has probably been your primary experience of computational science work. But that is not a sustainable or a growth pattern, a way of doing things. You have to introduce something else. And so the notion of a team of teams is really important. There's more than one way to organize. Oh, now it's on my screen and not on yours. Okay, anyway. Okay, so there's more than one way to organize that. And so you can organize them together as a collection, hierarchically, or you can try to create a fully connected network, or you can try a hybrid approach. And so what we've been doing within ECP is, and the software technology with these 55 projects, is to try to create a hybrid approach, where you have point-to-point in some instances, but there's also a hierarchy involved in it as well. All right. So, again, this is kind of buzzwords, but what we're trying to do to scale these small teams is use the tools that we have. We make use of Atlassian tools, Confluence, Jira in particular. We make use of BlueJeans for video conferencing technology. These are all tools that allow us to communicate on a very large scale to a large group of people instantaneously, simultaneously. And so we've been able to use those tools to create, again, buzzword, a shared consciousness. We can get information out there very quickly and uniformly that everybody can see, everybody can hear. And it's really important for us. We would not have been able to do this 10 years ago. Okay, we have to understand that these technology platforms we have are incredibly valuable, because without them, we could not scale a team of teams like we're trying to do. Another important element is eyes on, hands off. Okay, so we can see all the activity that's going on, but we'd rather use a shared consciousness model that allows people to make their own choices and do that based on their understanding of what we're trying to do, rather than dictate their activities. So that's really important to us. And that's this notion of empowered execution. Being able to tell people, and we're really trying to do this. We're trying to instill the culture within ECP ST, Software Technology, the ability for team members to make choices on their own. Since we share an idea of what the project's about, can you go on and do it without checking in with your leadership in the process? It's not just independent Wild West stuff. It's really disciplined, but it's disciplined on a shared notion of what the project is about, more than checking in with management. All right. So realizing this on ECP projects, what we're trying to do here is an important leadership and strategy for trying to make ECP as software technology what it is. And let's see, my last slide of content is this notion of a gardener, right? Again, I'm trying to put into your heads metaphor, ideas that you can use to guide your own activities. And so I think a gardener is a really nice example or story for thinking about how, if you want things to grow, you create the conditions for them to grow, right? And not be in charge of dictating how it grows necessarily, but just provide the right conditions. Okay, so this humbler gardener model, I think, is helpful, at least to me. Okay, and then my last quote, and then a bit of a summary. Okay, so I'm not a historian, but I like history. And one of the quotes that is really I've thought about from time to time is by a fellow Shelby Foote. He was a historian on the U.S. Civil War. And he said, before the war it was said, the United States are. Grammatically it was spoken that way and thought of as a collection of independent states. After the war, it was always the United States is, as we say today without being self-conscious at all. That sums up what the war accomplished. It made us an is. And so what we're trying to do with our activities in SDKs and aggregation is to make ours into is's. That's what we're trying to do. Okay, summary. So ECP is ushering a new era of computational data sciences. We have a lot of activities going on. This is a singular moment in history, and we relish the opportunity it presents. ECP Software Technology has a lot of products to which we're contributing. Some of them you know well, others are new. And I like this notion of team of teams, the shared consciousness, the power to execution, and converting R to is. All right. You thought you got away from the quiz, but you didn't. All right. All right, so exascale systems will have more network connected nodes than previous supercomputers. True or false? Be brave. False, right? In fact, we're actually shrinking. Okay, top performance will require roughly yes or true or false. That one you should know, right? True. Will you need to know how to write task parallel code? Some of you probably most know. How about vectorization? Yes. How about, is MPI the most important part? No. Okay. Is the X part most important? No, neither is, right? Because it's the plus. Will you need to know to be part of a large team? Yes or no? Probably yes. Will you need to know to be part of a small team? Yes. Okay, is the United States plural? No, we don't say it that way, right? Okay, and gardening is relevant? I think that's true. All right. Thank you for your time and attention.